Now we have a next thing is the so that this j 1 by 2 of x is equal to 2 by pi x into sine x. The sine x is actually an elementary function. So that's why this is another way is to looking at that express j 1 by 2 of x as a elementary function. Let us try to give the solution for this. We note that the jp of x, that is the Bessel's function, is written as n running from 0 to infinity minus 1 raised to n upon n factorial into n plus p factorial x by 2 power 2n plus p. Now here we have to calculate what is j 1 by 2 of x. So we'll substitute p equal to 1 by 2 here. So if I substitute p equal to 1 by 2 here, we get j 1 by 2 of x, which is summation n running from 0 to infinity minus 1 raised to n upon n factorial into 1 by 2 plus n factorial x by 2 power 2n plus 1 by 2. Now, what is the value of this? So it is a square root. So I can write down this is x by 2. So this is I can write down. So I'm multiplying and divide here 2 by pi x square root of 2 by pi x. So I'm multiplying and divided this quantity. So that's why what has happened is x by 2 combined with is x by 2 power 1 by 2 is there. So that's why this is 2n plus 1 you will have. And then root pi I am writing separately. And this quantity I am taking out. So that is 2 by pi x summation n running from 0 to infinity minus 1 raised to n factorial into root pi upon n factorial into 1 by 2 plus n factorial x by 2 power 2n plus 1. Now what is this quantity? Let us look at this. So now what is this n plus 1 by 2 factorial? As per the notation, this is gamma n plus 1 by 2 plus 1. So that is gamma, and we know that the gamma n plus 1 we can write down n into gamma n. So as per this we can write down this is n by 2 into gamma n plus 1 by 2. Further, using the same identity, we can write down this is n plus 1 by 2 minus 1 into n plus 1 by 2 minus 1, which is gamma minus 1 by 2. So finally, what we have is n plus 1 by 2 factorial will be gamma, or I can say n plus 1 by 2 into n minus 1 by 2 gamma n minus 1 by 2. Further, you will do the same thing. You will have n plus 1 by 2, n minus 1 by 2, n minus 3 by 2, gamma n minus 3 by 2, and so on. If you go on and on, what will be the last term you will have? if you apply this things, then it is n minus 1 by 2, n minus 3 by 2, the next term is n minus 5 by 2, and so on. The last term is left with 1 by 2 and the gamma 1 by 2. And we already know that the gamma 1 by 2 is root pi that we have calculated. So this is n plus 1 by 2, n minus 1 by 2, n minus 3 by 2, up to so on 1 by 2 into root pi. So this is, if you simplify, this is 2n plus 1, 2n minus 1, 2n minus 3 up to 1 upon this 2 into 2 into 2, n times, n plus 1 times will be there, because this is starting with n plus 1. So this is 2 power 2n plus 1 into root pi is there. So if I multiply and divide by this 2n here, so here I'm multiplying 2n, divide by 2n. Here I'm multiplying 2n minus 2, divide by 2n minus 2, and so on. Here I'm multiplying 2, here is 2, divide by 2. So if you multiply and divide by this quantity, then the numerator will change to 2n plus 1 factorial. So that's why this is n plus 1 by 2 factorial will be, you will have, it is 2n plus 1 factorial into pi, into root pi. So that we have root pi here. And then the denominator you will have 2 power 2n plus 1 into 2n, 2n minus 2, 2n minus 4, up to so on, up to 2. Now we'll just take out this 2 common out from each and every quantity. So that's why, no, this is not 2 power 2n, this is 2 power n plus 1. That is, we have here 2 power 2n, I have written 2n. This is 2 power n. And this 2, 1 times 2 is common out. So it is, you will have 2 power 2n plus 1 factorial root pi, 2 power 2n plus 1, and the left is n into n minus 1 up to 1, and which is n factorial. Now if you substitute these values, that is 2n plus 1 factorial into root pi upon 2 raised to 2n plus 1 into n factorial. That is the value of this quantity, 1 n by 2 factorial. Now, so this is j Bessel's of Bessel's function, that is j of 1 by 2 x will be summation n running from, so previously it was the square root of 2 by pi x is there already, summation n running from 0 to infinity minus 1 raised to n into root pi upon n factorial into n plus 1 by 2 factorial into n plus 1 by 2 factorial. The value is this, so I'm just writing that value, that is 2 plus 2n plus 1 pi into square root of pi into 2 raised to 2n plus 1 into n factorial and into x by 2 power 2n plus 1 is already there. Now you just observe that this square root of pi is cancelled out, n factorial is cancelled out, this 2 power 2n plus 1 is factorial cancelled with this, so only quantity is left, it is square root of 2 by pi x summation n running from 0 to infinity minus 1 raised to n upon 2n plus 1 factorial into x power 2n plus 1, and this is exactly, this quantity is exactly the series of sine function. So that's why this is equal to square root of 2 by pi x into sine of x. and which completes the proof of this expression. Similarly, I'm giving you an exercise here to prove that, so that Jacobian of Bessel's function of this 1 by 2 minus 1 by 2x is equal to square root of 2 by pi x cos x. This is the exercise I'm giving you as a homework. Now to prove this means expression as we have did it here, you have proved that gamma plus 1 by 2 factorial is this expression. So here, this is the hint that you can try to prove first that n minus 1 by 2 factorial will be 2n factorial into square root of pi upon 2 power 2n into n factorial. So this also I am giving you as a homework to check. To prove this one, you require to do this. Okay. So that I'm giving you as homework. You can try to see what is the things we have. And using this recurrence relation, we can able to find out also what is the value or what is the recurrence relation about the, so the question is express Bessel's function or j 3 by 2 of x and j 5 by 2 of x in terms of elementary functions. So the converting this j 3 by 2, as we have converted j 1 by 2 in the elementary function, now the question is to convert this into the elementary function. And we have discussed the one recurrence relation. So we shall use that recurrence relation here. So we shall use the recurrence relation, that is j by 2p by x, jp of x is equal to jp minus 1 of x plus jp plus 1 of x. That we have just previously we have used that one here, or I have given you as a homework to do that. This is the sixth one that I'm using here. This is the things I'm using. So that's why jp plus 1 of x, I can write down that is equal to so therefore jp plus 1 of x is equal to 2p by x jp f x minus jp minus 1 of x. That is exactly this I'm making. This is the equation. Now substitute, if I want that 3 by 2, then I have to substitute here p equal to 1 by 2. So put p equal to 1 by 2. We get this one, that is j 3 by 2 of x. This is we got 2 by x, j 1 by 2 of x minus j minus 1 by 2 of x. So this is the expression we got, and we already have the value of j 1 by 2 of x and j minus 1 by 2 of x. So if we use that one, a 2 is also cancelled out here. Yeah. So this is 1 by x. So this is 1 by x into square root of 2 by pi x sin x minus 1 by 2 by pi x cos x. So you can take common out the quantity. The first one should note that this x is cancelled out. I just take out this 2 by pi x common, square root of that. Inside left is sin x upon x minus cos x. And to get this j 5 by 2 of x, we'll substitute p equal to 3 by 2 into this equation. So I'm just calling this equation as a star. So putting p equal to 3 by 2 in star, we obtain j 5 by 2 of x, that is 3 by 2 plus 1. This is 3 by 2, also substitute 2 will be get cancelled out. So this will be 3 by x, j of 3 by 2 of x minus j 1 by 2 of x. So this is 3 by 2, j 3 by 2 of x, which we have calculated from this, that is square root of 2 by pi x sin x upon x minus cos x. J 1 by 2 is square root of 2 by pi x sin x. And if you just take out this square root of 2 by pi x common, then we will have this is square root of 2 by pi x inside bracket. We will have 3 by 2 sin x by x minus cos x minus sin x. So this is the j 5 by 2 of x in terms of Jacobian function.
Sir, it is 3 by x in second equation.
Yeah, this is 3 by x. Yeah. So this is 3 by x. So this is this Jacobian of 5 by 2 of x in terms of elementary function. We can also use this previously used another expression, that is, if you want that, you can also use the other expression, that means by putting p equal to 1 by 2 in this or 3 by 2 into this. That is 3 by 2 plus 1 is also getting, yeah, we have to done this one, the same thing. Okay, no problem. Yeah. So I'm not saying that something else. Fine. Now I'm giving you just expression. Just given you some exercise here. That is the next one. Is the same kind of things I'm asking you, that express j of minus 3 by 2 of x and j of minus 5 by 2 of x in terms of elementary function. So do this. The hint is the same thing which we have used in the previous example. That means this expression star. You have to substitute some particular values into star. So we'll start with that. We have, that is, from star we can write down jp minus 1 of x is equal to 2 by 2p by x jp of x minus jp plus 1 of x. Because here it is jp plus 1 is the equation head, but here I want that it is in terms of minus 3 by 2, so that's why I put it jp minus 1. I call this as a double star. Now put P equal to minus 1 by 2 in double star. We obtain j minus 3 by 2 of x. This will be minus 1 by x, because if I substitute p equal to 1 by 2, minus 1 by 2, we'll have minus 1 by x. J minus 1 by 2 of x minus j 1 by 2 of x. So this is minus 1 by x, j minus 1 by 2 of x, which we already have write down in terms of cos. So that is 2 by pi x into cos x minus 2 by pi x into sin x. So just take out this square root of 2 by pi x out. So if I take minus square root of 2 by pi x out, you will left with cos x upon x, because that is the things we have, and the plus sin x. So this is Jacobian of minus 3 by 2 of x in terms of elementary function. Similarly, if putting p equal to minus 3 by 2 in double star, we obtain, that is, in this you just substitute p equal to minus 3 by 2. You will have here it is j minus 5 by 2 of x equal to 2 into minus 3 by 2 upon x, j minus 3 by 2 of x, that we have here, and minus j minus 3 by 2 plus 1, so it is minus 1 by 2. So minus j minus 1 by 2 of x. Minus j, sorry, j minus 3 by 2 is this value. This 2 is cancelled out. So this is minus minus become plus 3 by x square root of 2 by pi x. Inside bracket you will have cos x upon x plus sin x. Minus j minus 1 by 2 is square root of 2 by pi x cos x. You can just common out this square root of 2 by pi x. Inside bracket you will left with 3 by x cos x upon x plus sin x minus cos x. So this is this Bessel's function at point minus pi by 2 is in terms of elementary function. Let us discuss some more examples. So that these are the very short, small exercises are there. So that Jacobian of minus 1 by 2x is equal to Jacobian is minus 1 by 2x into 10x. So ultimately I have to prove that this upon this is 10x. So if you know this value of this, you can easily prove that. If not, you just start with the Jacobian of 1 by 2. This Bessel's function at 1 by 2 is this, which can be expressed as 2 by pi x into sin x. So you just multiply and divide by cos x here. So what is this quantity? It is 10x. So we'll have the square root of 2 by pi x into cos x into 10x. And this quantity is exactly the Jacobian of minus 1 by 2, or Bessel's function at minus 1 by 2 into 10x, which completes the proof of that. The next one is, the question is to express, let me do it in the next slide, that is express j4 of x in terms of j0 of x and j1 of x. Now we have to do this. So from the recurrence relation we have of jp of x, which we have expressed as equation number 6, which is jp plus 1 of x is equal to 2p by x jp of x minus jp minus 1 of x. Now, since I need 4, I just substitute p equal to 3 in star. We get j4 of x will be 2 to the 6 upon x, j3 of x minus j2 of x. Now here, this is j3 and j2. I want to express this is in j0 and j1. So in this recurrence relation, star will gives you further simplicity. So putting this j equal to 2 here, we'll have the next quantity, which is putting p equal to 2 in star, we get j3 of x is equal to 2 into p, that is 2 to the 4 by x, j2 of x minus j1 of x. Still here is j2. So that's why by putting p equal to 1 in star, we obtain j2 of x, that is p into 1 by x. So it is 2 by x, j1 of x minus j0 of x. Now you can substitute this all the value. That means I can say this is equation 1, equation 2 and equation 3. So you just substitute first equation 2 in terms of in sorry equation 3 here in equation 2. So from 2 and 3 we obtain J3, actually J3 in terms of J0 and J1, that is 4 by x into 2 by x, J1 of x minus J0 of x minus J1 of x. That is the value of J2. So if you simplify this one, you will have 8 x square J1 of x minus 4 by x J0 of x minus J1 of x. So if you simplify this one further, then you will have J3 of x is equal to 8 by x square minus 1, 8 by x square minus 1 into J1 of x minus 4 by x, which we have here, J0 of x. If I call this as equation 4, and now using the equation 1 and 4, the equation 1 that is the value of J3 and J2. You substitute this value of J2 and J3. So that's why I'm required equation 3, and also I required equation 2 and 4. So I required equation, so from 1, 2 and 3, and 4, we get J4 of x is equal to The J4 value is 6 by 3 J3. J3 we already have calculated in terms of, so it is 6 by x J3. J3 is this value, 8 by x square minus 1 J1 of x minus 4 by x J0 of x plus, sorry, minus J2 is there. So minus J2, the value of J2, which we already have calculated in terms of J0 and J1, that is 2 by x, J1 of x, minus minus plus J0 of x. That is from this. Now combine this all the terms. That is 6 by 8, sorry, 6 by x, 8 by x square minus 1 minus 2 by x, J1 of x minus 24 by x square plus 1. So if I multiply inside, if I take minus sign outside, then it will be this J0 of x. So this is the final answer, which is in terms of J0 and J1. So these are the properties of Jacobian functions are there. In the next lecture, we'll discuss about what are the orthogonal property of this Bessel's function, which we will discuss in the next lecture. So if you have any question in this lecture, you can ask.